All right, let's take a look at section 12.5, which deals with the normal distribution. All right, so there's several things we're going to be trying to do. The main one is to convert between z-scores and normal curve areas, which would also have something to do with the probability of data values being in a certain spot. And we're going to learn to interpret what these values we're getting out of a z-score table really tell us. Okay. So real quick, let me just go ahead and go through this earlier part. All right, so a discrete random variable is one that can only take on certain fixed values. The example I used here was the number of heads and 5 tosses of a fair coin. You can't get 1.5 heads. All right. So then this diagram shows the probability distribution for that. So the height of the bar would be the probability of getting that many heads in 5 tosses of a fair coin. So the probability of getting 2 heads when you toss a coin 5 times is what's given by that height of the bar. All right, now the shaded area in this case represents the probability of getting 1 or 2 heads. Okay, so the graph that we see there is a probability distribution. Okay. All right, now that was a discrete random variable. So we use like those bars to represent what the probability would be for each of those possible outcomes. All right, now a continuous random variable I should have had the word can in there, can take on all real values over some range. Like you can get those in-between numbers. All right, for instance, if we are measuring the diameter of a camellia bloom, then it could be 7.23 centimeters. Okay, it could be some number in between. We could still look at a graph that represents it's like a probability distribution. It's like we had a bunch of camellias and we measured them, and when we took their measurements, maybe there were this many that were 5 centimeters, maybe there were this many that were 10, this many that were 15, 20, 25, and all the in-betweens, right? So think about the height here being camellia blooms that we found to be these various measurements. And that would create a graph of the data values, okay, that would show you how those are distributed and see how most of the blooms are around 15 centimeters. That's the mean. All right, and then what you see shaded on this one, this region right here, would be the area under the curve from 16 to 21, but it would represent the probability that a camellia blossom would be between 16 and 21 centimeters. So if I randomly selected a camellia blossom, the probability that it would be between 16 and 21 centimeters, okay, would be what that area under the curve represents. All right. So let's think about whether something's discrete or continuous. The heights of pine trees at 5 years of age, that would be continuous. But the number of children in a family, you can't have 1.5 kids, so that would be discrete. Okay. All right, I also want to look at, I don't know why that moved. Okay, I also want to look at the empirical rule in this formula. All right, so let's take a look at that. There we go. All right, so normal curves are used quite a bit. They're very important in statistics. All right, and a lot of continuous random variables have a normal distribution, and discrete ones are distributed approximately normally. Like think about this one here. If I smoothed it out, it kind of has the look of a normal curve. That symmetry, that highest, the center being where the highest occurs. All right, all of these are normal curves. They're bell-shaped. They're symmetric about some center. Okay, all of them have a symmetry to them. I could fold up the two sides. And the mean, median, and mode of a normal curve are all equal, and they occur right there at that center. Okay. And then the one you see in red, that's actually the standard normal curve, where we've standardized things to fit this certain curve. Now, there's a rule. It's called the empirical rule, or the 68, 95, 99.7% rule, that says this: if you have a bunch of data values that are normally distributed, okay, then about 68% of them are going to fall between this would be one standard deviation below the mean to one standard deviation above. Okay, this line right here would be 2 standard deviations below. This one would be above, and this one would be 2 below. And then here, 3 below and 3 above. So the labels I'm doing right here represent the standard deviation. And see, a standard deviation, this is 1 standard deviation, so then this would be 2, this would be 3. And those are positive because they're above the mean, and then these are negative because they're below the mean. All right, so this rule of thumb says that about 68% of the data values will fall between 1 standard deviation of the mean, above and below. 68% would be there. And then see, from 2 below to 2 above, about 95% of the data values, and then almost all would fall from 3 below to 3 above. All right, so if it tells us we can use the empirical rule to answer a question, then you should think about that 68, 95, 99.7%. All right, so we want to know the percentage of the area under the normal curve that would be above the mean. So think about the normal curve. The mean is right here in the middle. We want to know what percentage would be above it. Because of symmetry, we know 50% would be above it. What's underneath the whole thing would be 100%. So here's the mean right here. So 50% would be above it. Okay. All right, between the mean and 1 standard deviation above the mean. That's what we're trying to do now. So think about what that would look like. Okay, mean, and then you've got your little standard deviation lines. We want just this right here. Okay, what we know is it's associated with 1. So 68% would be between -1 and 1. And because of symmetry, this should be half of that. Okay, so 34% of the data values we would expect to be between the mean and 1 standard deviation above. All right, now the wording of this is a little confusing. I'd have to work on that for a test. Okay, so more than 2 below the mean, what I meant by that is out here. Okay. All right, so see how they use 2. So in your mind, you should be thinking it must have something to do with 95%. So 95% of the data would have been here, between two standard deviations above and below the mean. That would be 95% here. So that means outside, both there and there, should be 5%. And then you just want one tail, right? So then this part, just that part, would be half of the 5%, which would be 2.5%. Okay. Okay. All right, let's look at these two problems. So we have 280 students taking an exam. We're told that the distribution of their scores can be treated as normal, so we're thinking this. Okay. We're supposed to use the empirical rule to find the number of scores falling within 2 standard deviations of the mean. So that means in here, from -2 to 2. So that should be 95% of the scores approximately. So we want the actual number of scores, not just what percent. So we need to take 95% of 280, which is 0.95 times 280. And that turns out to give us an estimate. We would expect 260 of the students to have scores, okay, that would be within 2 standard deviations of the mean. Okay. All right, now this one we have a trout problem where we have this lake that has about 6,000 fish, and they tell us the trout are distributed normally, but they don't tell us, they don't ask us a question like how many would be between 1 and 2 standard deviations from the mean. Okay, instead it gives us a raw data value, a length. Okay, so we need to kind of think about where those fall. So 12 is the average, so it would be here. So this is your X bar, that's the middle. This is your S. So what you can do is think about being 1, 2, oops, let me draw that guy again. Okay. 1, 2, 3 standard deviations above the mean. You could just go and add 2.65 each time. So this would be 14.65. Then if you add another standard deviation to that, you'd be at 17.3 standard deviations above the mean. And we could keep going, but that's what I was noticing is really I don't need to add another one. All right, and then let's see where if 6.7 falls at a standard deviation line. Okay. So 12 minus, so if you subtract 2.65, you'd be at 9.35. Then if you subtract 2.65 again, you'd be at 6.7. And then if we did it again, we'd get our third percentile, but I needed 6.7 and 17.3. All right, I had to make that type of thing happen on this question because you're going to be using so that you could use the empirical rule. So what we found is this was at a z-score of -2, this was at a z-score of +2. So we would expect, again, approximately 95% of the fish to be between those lengths. And there's 6,000 fish, so we just need to do the 95%, 0.95 times the 6,000, and that tells us there'd be about 5,700. We would expect about 5,700 trout to fall between those. So, you know, if you caught a trout that was like 19 inches, then that would be one that's rare. It would be way up there, past the 2 standard deviations above the mean.